the other day I bought the Programming Quantum Computers book from O'Reilly, and I'm gonna do a review on the book really soon. I think, in general terms, I think it's a really interesting. It has its pros and cons in my opinion, but I think it's a really well thought through introduction to quantum computing. And I would definitely recommend that you buy the book. But I was just reading through, and then I came across the swap test, which kind of blew my mind. And I want to explore this a little bit more because it's one of those, again, sort of intuition benders or mind blowing, mind bending thoughts. The concept is you've got three qubits, or you've got two qubits, right? That you want to know and want to check whether they are equal or not, but you of course cannot measure them, because if you measure them you're going to destroy the quantumness. So the concept of the swap test is by adding sort of a third qubit here and performing a Hadamard and a control swap and then another Hadamard and a not, then you can know whether they're like how similar they are, so to say. So you're not going to get 100% or always an 100% sort of measure on that, but you can know how similar they are. So this is, and I wanted to sort of try to understand that, because if you think about this, and how is it possible that a qubit that apparently has no interaction other than being a control of an operation on the other two qubits, how can that be, right? And at the end of the day, this is because of the fact that in quantum computing um, you cannot just reason about a subsystem or a part of your circuit in the same way you would do this in classical computing, because what you know here, what you see is the overall system of three qubits, and that's what you have to consider. So, and I'm going to try to. So I just started now here with the IBM Q experience to try to play with that. I just googled how to implement a control swap, and this is the way that you do it. I'm not going to get into exploring that right now, but I wanted to understand what's happening really here, right? Because if those two qubits are zero, as you can see here, and then I do what they say, and I just do that, right? I mean, you see that it's 100% one. So, and this is actually pretty cool. This means if I add an x and an x, right? So they're also now equal. It's also 100% one, and we're taking a look just at this bit here, or this qubit here. Whereas if you make them not equal, like 0 and 1, then you got a 50-50% chance of seeing a 0 and a 1, which is, I think that's, I mean, I'm not going to show the rest of the content of the book. You should definitely buy the book if you really want to read it. It's super interesting. I think it's only available as of now, as I'm recording in an ebook form, but it's pretty interesting. So, but I think that's what they say here is that the circuit is not gonna. So it's gonna tell you if you have 50% chances of seeing a 0 and a 1, then you know that they are absolutely different. I think that's the key. Um, so the reason is the reason here is, as soon as you see a 0, you know they are not 100% equal. But then you can tweak, you can play with the probabilities and see how much different the percentage thing. At the end of the day, I think what this whole thing does is the percentage of the probability of measuring a 1 for the qubit 2, so for the last qubit here, is the probability, is the sort of the same. It's equivalent to the degree of similarity between the two qubits. Exactly. So I wanted to understand why. And let me open the notebook, the notepad, because I think that's so. I think that's one of those moments where my sort of checking that by hand, following two examples, could be an interesting example of how this works and why this works. Because I suspect this is again a game of positive and negative uncertainty, which is a concept that I explored a little bit in the beginning of when I started doing the videos for the channel, and I think it's definitely something. Um, that it's really powerful from at an intuition level. So I'm gonna do an example first where we have 0, 0, 0. Let me see if I can zoom that in. Right, so 0, 0, 0. That's our starting state, and then we're gonna do here down like a okay. I will just reuse. We'll do one with 0, 1, 0. Right, so here we expect that they are equal. I mean, they are equal here. They are not equal. You can get more complex than that. Those qubits can be superpositions and whatnot, but we're not. I'm just at the intuition level. I want to see what's really happening in here because it's not obvious, right? It's not obvious how is it possible that that this is detectable by measuring the qubit 2. I'm assuming the first thing first, I'm assuming we can ignore the x here because I think that this x is just to flip the meaning and then have a 1 when they are different versus 0 when they're not different. So I think we can really ignore that for the moment for our reason. So we can kind of stay here. So it's a Hadamard, a control swap, and a Hadamard. That's what we want to do, right? And the Hadamard is only on this qubit here. So the first step is that's distracting me. So the first step is performing a Hadamard here, right? So if we perform a Hadamard here, then we have this state. And again, if you remember well from my early videos, I'm not using the full state vector. I'm not putting in here the amplitudes or whatever. I'm just playing with the possible states roughly because just to keep it simple. Because this is one of those examples where we're not getting into weird states, but we're just rather staying in, kind of like equal superpositions and stuff like that. So plus and minuses, and then things cancel out. And I think that's it's more lightweight to do it this way, and it's even nicer than just following the circle notation that is introduced in the book, which is it's a pretty nice notation, but it's a bit heavyweight sometimes to have some quick reasoning about stuff. So we've applied a Hadamard. Now we apply a swap, right? So the as you can see here, doesn't matter. Here we're not going to apply a swap in this case because there's a 0, right? So we stay 0, 0, 0. So let's maybe right here. This was the Hadamard operation, right? Here we do a I'll write control swap like that, or it's a swap, but it's a control swap. In this case, because there's a 1, then we swap, but because it's both zeros, is effectively the same. And I think that's exactly the difference. And you can see here, I think I get it. So let me explain what I sense. Imagine we have that case. So I just stopped by because I think that's the point where the difference is visible. Imagine we have this, right? So if this is what we have, then we also have, so we have this here and this here. Now the difference is because here we make a swap. So this stays the same because it's the 0 in the control, so we don't make a swap. But in this side of things, then we make a swap, so we actually have this. And now when you will apply the Hadamard again, because the Hadamard is now going to create negative uncertainty because there's a 1 here, basically what this will what this will cause is that here probably, because we haven't swapped, some of the stuff is going to cancel out, so you're still going to have a majority of zeros. And here, because you have flipped the things, it's not going to cancel out anymore, and so you're going to still have some 1s laying around. I think that's the idea. So if now we apply another Hadamard here, so this, and remember now we have to do it for each of these ones. So this turns into 0, 0, 0 plus 1, 0, 0. Maybe let's zoom out a little bit. And so this is how we've expanded. We've expanded this first part, the 0, 0, 0. And now we're going to expand the other part, which is going to be a 0, 0, 0 and a minus 1, 0, 0. Remember that a Hadamard and a 1 creates negative uncertainty. So I mean, or you can call it a negative phase, but I like the word negative uncertainty. It's pretty cool, actually. So as you can see now, those things cancel out. So here we've got a plus 1, 0, 0 and a minus 1, 0, 0. And the reason they cancel out is because this hasn't changed, right? So at the end, when now we have sort of the result of the whole thing is that we have basically 0, 0, 0, right, as the only possible state that we can measure, because those things cancel out, and then we've got twice the same state. So literally, you have 100% chances of measuring a 0. Then you apply the x, and then that turns into a 1, right? So that's obvious. But now if we do the same here, maybe move this a little bit this way. So if we now do the same here, we're going to see that basically, let me see, we apply another Hadamard. So now we're going to have this here, right? So this is what we want to expand. So this, it's expanded like this. And the second component now is going to be expanded as well, also with negative uncertainty. So we're going to have first a positive 0 and then an actual negative 1, right? So now you see that those things, which in this case would cancel out, those two components don't cancel out because we've swapped them, and they were different. That's the essential. We swapped them, and they were different. So essentially, here, really, all you end up with as a result is that you've got a. If we just take a look at this qubit here, we literally got, and the minus sign doesn't matter here, we've really got a 50% chances of measuring 1 and 50% chances of measuring 0. So, and this is exactly what I was reading, that this is what you, when they are different, you're gonna have that result. It's not that you're gonna have like 100% 1, right? So, and I mean, in this case, when you apply the x, then you flip that, but those don't matter, and then here you flip that, but that doesn't matter as well. So, but that's the idea, and that's how this works. Really, there's no magic in the sense that, you know, the real trick, or the real quantumness here, is the fact that we have a full system, and we cannot break down. So we cannot just simply take a look at 2 qubits and 1 qubit separately and then think of, oh my god, what's happening here. It's just 1 qubit and it's just acting as a control. How can that change? Like, how can something like that happen, right? Classically, that would be just weird. So but from a quantum perspective, because of all the interference physical effects that those qubits go through, you cannot take a look at each part separately. I mean, you can, but it's but then you cannot basically break it down so like straightforward. So in this case, you can see that when you take a look at the 3 qubits at the same time, not at just 2 qubits and then another one. So it's all the time you're working with the 3 qubits, and then statistically that's what you get at the end. So this is pretty cool. This is pretty cool. So I was not far away from. So I think that's my thought process here was quite okay. Yeah, and that's basically what you're going to see. I mean, I can try to measure that. If I now run this, let me just say that I want to measure this, and I just want to have 1 qubit here, 1 classical qubit. So I'm going to measure this. Why there's a 2? I want to have just 1. Okay, and now I want to measure, and now I'm basically gonna call this the swap test. I'm gonna save it. I'm gonna save the circuit, and I will hopefully I can run it on a simulator. So now, because they're different, we should see 50-50. So 50% of seeing 1 and 50% of seeing 0. Cool. Let's see. Blah blah blah. Yeah, 50-50. Beautiful. And that's how you could that's how you can determine whether two qubits or how two qubits are similar. I think, and I will explore that further, I think this is a really useful intuition, a really useful concept for quantum machine learning and quantum AI stuff. But I'm not so sure exactly where. So I'll definitely take a look further at this topic. But this is basically a really, really one of those other topics where the quantumness is a bit mind-bending at the beginning. But if you take a look and you break down what's happening within the circuit, then you understand why this is happening. So pretty cool stuff.